Hello, my name's Andres. I work with Amazon Fulfillment Technologies. So we have a number of different teams here that we support. It has to do with big data type of problems, Amazon robotics, rapid prototype team, new team that we're getting, Make on Demand. But a quick show of hands real quick, how many of y'all, who's like first time here with us today? Wow, a lot of new hands. Welcome, welcome. I'm going to keep it short and sweet. I know y'all came out here to see Jonathon, but if y'all have any questions, my partner Katie, she's at the back of the room, so she's one of my recruitment partners. Our emails are up there on the board, so if y'all have any questions, y'all want to connect with us afterwards, feel free to stick around and talk to us or connect with us online. And thanks so much for coming.
All right, thanks Amazon.
Thanks everybody for the introduction. Thanks Austin Data Geeks. Thanks you all for coming out. My name is Jonathon. I changed the title of the presentation a little bit from what was listed on the meetup. I just thought it needed to be a little punchier. But we are talking about computer vision. We're kind of talking about Nazi hunting. That's a little bit over the top. But this is the area that we live in now. You know, this is the age of being over the top. This talk is going to be huge. It's going to be tremendous. The best talk that ever talked. So this is a little bit of background about me. I'm the CEO of a company called New Knowledge. We're also hiring. Don't tell Amazon. I'm the co-host of a podcast called Partially Derivative. It's about data science, also about drinking, because those things often go hand in hand, especially if you're good at data science or drinking. My background, all the logos at the bottom, mostly are just there. I tend to come at this stuff from more of a social science background. My research background is on kind of discovering extremist communities online. So have published some work on discovering ISIS communities with the Brookings Institution, and then also advised the White House and State Department, but again, around this idea of like discovering extremist communities, how they operate, why they operate, who they are, that kind of thing. So yeah, that's background. All right, so let's get started. What is computer vision? So actually, before we really dig into the details, so I kind of know how to pitch this, who is everybody here like a machine learning practitioner? Like who actually uses machine learning in their jobs? Oh, good. Okay, cool. So I'm not going to get into like the raw mechanics of neural networks because that seems like it would bore the crap out of about half of you. Okay, so this is good. This is perfect. I know how to pitch it. All right, so what is computer vision at a basic level? So we're talking about what it means for computers to be able to see. So when we see this, we see Abraham Lincoln. We know who Abe is. Pretty quickly. We can recognize them right away. But that's not really how machines see the world. So when we talk about computer vision, we're actually talking about the way that a computer can break down this digital image into something that it will understand. And that looks more like this. So when a machine sees the image, it breaks it down into a bunch of pixels. There's different pixel intensities. So that image in the middle is like an intensity score, the lightness or darkness of the image at that location. And then on your far right, that's a matrix of pixel intensities. And so ultimately that's the thing that we care about, is this matrix of pixel intensities. There are some models that can actually understand this with a little bit more sophistication. They can actually use like RGB values, red, green, blue values. But for the purposes of this, we can just focus on kind of straight up pixel intensities. So the computer's goal is to get a matrix of numbers that allow it to understand this thing that it's looking at. So it's translated Abe into a bunch of numbers. Okay. From there, we can look at patterns of pixel intensities in this matrix and use those patterns or use those kind of clusters of pixel intensity values in our matrix to pull out features, and then we'll use those features in order to classify the image. Right? So like a supervised machine learning problem, for everybody who's not a machine learning person, means that we give the computer a bunch of examples of the thing that we're interested in, and then it learns to be able to recognize that thing in the future. Right? So if we gave it a bunch of pictures of Abraham Lincoln and said, hey, this is what Abraham Lincoln looks like, find the patterns of pixel densities, extract the right features to be able to recognize Abraham Lincoln versus somebody else, this is what that process would look like. Cool so far? All right. Okay, so just to recap, photo, it represents as a pixel intensity matrix. We pull out some features from that, and then we make predictions. Awesome. So there's two kind of big buckets when it comes to computer vision. One is object recognition. I think when you hear about computer vision in the news, about kind of Google research or Microsoft research or really cool, exciting things about automatically giving images captions or AI that knows how to dream, they're kind of in the deep learning object recognition realm. And so there's a bunch of different images of a cat here. It's actually really complicated to recognize a cat in all of these different contexts. There's like a regular cat, the kind of cat that you think of in a cat commercial. There's a cat wearing a suit, which doesn't make any sense at all. There's a cat freaking out because it's afraid of cucumbers in a totally unrealistic way, because I don't think cats can make that face. Nevertheless, as human beings, we'd all look at that and go like, oh, that's obviously a cat. Every one of those is a cat in every context. But the subtle differences that allow us to distinguish the fact that that's a cat from everything else need to be learned. It's really complicated. In addition, you've probably seen object recognition in practice when you upload a photo to Facebook and it says, hey, I've noticed that your friend Jane Doe is in this photo. Should we go ahead and tag her? The reason that it's able to not only recognize that it's a human being, but that it's Jane Doe is object recognition. Cool? Awesome. Very complicated, seriously hard, tremendously difficult, hugely important. Okay, the other thing is object detection. This is a lot more straightforward. This is pretty much taking a shape that appears more or less in the same way every time that you see it. Maybe it flips around, maybe it's inverted or whatever, but it's more or less the same. You don't really need to recognize it. You don't really need to understand the context in which it appears. You don't need to have the concept of the shape learned in order to recognize it. You pretty much just need to see the shape. And object detection is a lot more straightforward. It's the kind of thing that allows Facebook to draw that little box around your friends' faces when you upload the photo, even if it doesn't know who they are, because the face is a very recognizable standard shape. And it's a much more straightforward process. It's usually shallow learning instead of deep learning, so the kind of machine learning models that, that you'll find without needing to build big, massive neural networks. Okay, so object recognition, pretty complicated. Object detection, also pretty complicated, but a lot more approachable. So, object detection is the thing that allows us to go around hunting Nazis on the internet, as promised in the title of the talk. Okay, so a little bit of context, because you might be saying to yourself, Jonathan, that's cool. I mean, but why would I care about finding Nazis on the internet? Honestly, I'd prefer to stay very far away from these groups of people. And the reason is because I was telling you before, I study extremist communities online. And right around May, June, when all of a sudden white nationalists, the alt-right, and Nazis were suddenly part of a presidential election, I thought to myself, that's weird. I wonder how big these groups are online. Like, how big are these communities? Are these people really active online? And if so, what kind of impact are they having on the larger discourse? Are they a tiny fringe group of people that's having an outsized impact on the conversation? Or is it actually as if there's this huge movement of people who are very excited about a white ethno-state and concerned about white genocide and blah, 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 blah? They're horrible people. And so the outcome of this research was an article that I wrote for the Washington Post. And in that article, we looked at the language that was being used on the alt-right, kind of in white nationalist communities on Twitter. And the thing that we found was that the language that these groups are using is becoming more and more radicalized over time. So the language that they're using is becoming more and more like potentially violent rhetoric, which is concerning. Before we could make this discovery, before we could actually analyze the language of all these people, we had to discover enough of them. We had to build out a community. We had to find people. We had to find this community as they were operating online. And one of the ways I thought we might be able to do that was by computer vision, by actually looking at the way that the images that these groups were posting when they posted things to Twitter. So just to give you an indication of how aggressive this community is. So after this article was released in September, as you might suspect, I got a lot of attention from the alt-right on Twitter. So swarms of people sending me tweets telling me that I'm a horrible person, yada, yada, yada. And then this one in particular, where they took the time to Photoshop me into a cartoon gas chamber and then put Donald Trump's head on a cartoon German Secret Service person turning on the gas chamber. So they're you know, they're a creative group, and they're pretty aggressive. Like I said, they're horrible people. So, but the idea being is before, to even get to the point where we could do anything interesting with this analysis, we have to be able to find them in the first place. And one of the ways to do that is to analyze their language, look at the words they use in their Twitter profiles, look at the words that they tweet. But I think a very reliable way to identify extremists is to look at the symbols that they use. To look at the images that they post. So extremist communities are kind of like, you know how, we're probably not a big group of sports fans, let's be honest. I was going to use a Longhorns example. Well, this is even better. So we're probably not a big sports fans. But there's maybe that guy in your neighborhood who like paints his car burnt orange because he's so into the Longhorns, and like on every game day he dresses in burnt orange and he wears all the team uniforms and he knows all the players' names and he's always tweeting at the coaches and he calls into radio shows and he's kind of a fanatic. And everybody keeps their distance because boy is that guy weird, because he's so into the Longhorns. But then he meets somebody else who's as crazy about the Longhorns as he is, and all of a sudden they have this instant connection because this thing that's like a defining characteristic of their identity, this truly oddball, fanatical fascination with this thing, means that they have this like instant community, right? And that's pretty much the way that extremists are. So if he's like a Longhorns extremist, which is a pretty safe kind of extremist, truth be told, I mean, you know, with some caveats, unless there's some Aggies in the room, in which case, you know, he is what he is. But okay, so he's a Longhorns extremist, but anybody who has that kind of like fanatical association with an ideology tends to want to like brand themselves, display the fact that they're associated with a particular group because it's a huge part of their identity. And so they use symbols. And it's a lot like, you know, gangs use symbols, countries use symbols, everybody uses symbols. And these groups in particular will use symbols even when it is potentially dangerous for them. In this case, because it allows researchers to discover them on the internet, which, you know, in some cases could get them arrested. I thought, okay, so there's a lot of different symbols that white nationalists and other sorts of like far-right extremists use. The Celtic cross, the white power fist, yada, yada, yada. I thought as a test, just as a test, I would see if I could find people posting the swastika. Mostly because I think we can be pretty confident that if you are putting a swastika in your Twitter avatar, there's no like ambiguity about what you're doing. Okay, Nazis. Okay. Okay. So we're gonna look for swastikas in Twitter avatars. But this turns out to be actually kind of complicated, right? So there's different types of different ways that the swastika shows up. So this is a Twitter avatar. KKK 1488. All of those things, by the way, are like weird white nationalist code words. KKK is an obvious one. 14 words is whatever. Okay. But so he's got this really graphic representation of the swastika in the kind of lower left-hand corner of his avatar, amongst other kind of like white nationalist symbols. So that's one way that it appears. That's a pretty straightforward way. You can imagine like not a super sophisticated computer vision algorithm being able to identify that shape in this context. Not that big of a deal. But also, it shows up like this. So this fine young gentleman from the state of Tennessee is posing shirtless because he's tough, and he has kind of an obscured swastika that's tattooed onto his chest. And so we'd like to be able to identify the swastika in this context as well. Partially obscured, a little bit warped, not as graphic, and rotated. So it's a really different way that the symbol appears than in the previous case, but we want to be able to identify both. This is our task. So how are we going to do it? One way is deep learning. So deep learning is very trendy. Is everybody like, when you hear deep learning, do you feel a little bit cooler that you're talking about it? I certainly do. So actually, the funny thing is, the real reason that I decided to try and use deep learning when I was working on this is because I got invited to go give a talk because of the ISIS research that I'd done with a group called Lincoln Labs. Lincoln Labs is an MIT research group that works with the Department of Defense and they said, hey, Jonathan, your ISIS work, really cool, man. Can you come do a workshop on deep learning? And I went, well, to be honest, I'm not really an expert in deep learning. I'm really not your guy. And they said, that sounds fantastic. We'll see you in a couple weeks. And so in a state of panic, because I had to give a presentation to a bunch of experts, like literally some of the smartest data scientists in the world, about a topic that they probably understood that I didn't know very much about. So, okay, I thought, all right, I'm definitely going to use deep learning on this Nazi thing that I've been doing, because if nothing else, I can talk about it when I go meet all these Lincoln Lab folks. So a quick primer on what deep learning is. It's not super important that you understand all of this. As is clear, I don't really understand all of it. And truth be told, nobody really understands why deep learning is as effective as it is. In all seriousness, I'm pretty sure, right? Like we've yet, even in the academic literature, we have yet to discover concretely why this is so effective. Okay, so don't worry about it. Nobody knows. The smartest people in the world have no freaking idea why deep learning is effective. So the difference between deep learning okay, let me take a step back. Deep learning is just machine learning. It's based on neural networks, artificial neural networks, obviously. The difference between a regular neural network and a deep neural network is that a deep neural network has lots of layers. So in this simple one over here that I have up on the screen, we have an input layer, that's the beginning. We have that layer in the middle, the 3 circles, that's the hidden layer. It's not really hidden, we can see it, it's right there. It's just called a hidden layer. It's called a hidden layer because it's hard to understand what's actually going on. And then there's an output layer at the end. And that's usually the outcome of like the prediction. So if it's a class, these are usually classification problems. And so the output is like, the probability that whatever it is that you fed the neural network is class X or class Y or class Z or whatever. And that's it. And so the only thing that's important to understand at this stage, really, is that each neuron, so like let's say that each circle is a neuron, has to perform a calculation, and it gets a value from all of the neurons in the previous layer. So that's a lot of calculations when you're dealing with highly dimensional data like images. So if you have an image that's 100 pixels by 100 pixels, that means that there's 100 calculations at least that need to be performed by each neuron in each layer. And so when you have a deep neural network where you have a lot of layers, this quickly becomes really computationally expensive. So for highly dimensional data, high dimensionality data, high dimensional data, like images, there's a cool technique. There's a cool type of neural network called a convolutional neural network, which sounds even cooler than a regular neural network because it's got convolutional right in the name. Really what a convolutional neural network is doing is that it's actually just moving across the image in chunks, maybe like 5 by 5 squares. So it's looking at that kind of pixel intensity matrix that we talked about originally, and it's moving across the image and saying like, can I discover features that are meaningful in different parts of the image? And so ultimately the features that it discovers ends up being edges for the most part. And so it's looking for edges that are sort of like spatially in the same place in the image. And then once it has like collection, oh, here we go. Sorry, I have multiple slides about this. So you have your pixel intensity matrix, and ultimately you discover features that look like this, kind of on the far right, or yeah, the far right for everybody. So, and so it discovers these edges. These are the features that are ultimately used in the classification. And as it's looking for these features and kind of like clumping together in certain parts of the image that allow it to make a determination about what it is, it's like a higher level representation. So it's not just looking at pixel intensity values, like raw numbers from that matrix. It's looking at collections that are edges, and then it's ultimately trying to discover higher level features that allow it to make a determination about what it is that it's looking at. So you move from raw pixels to features like edges and lines, and then it's slowly starting to understand that it's looking for, in this case, layer 3 there are like maybe specific human faces. In our case, we would hope that by that point, that by layer 3, you'd start to see an actual like outline of a swastika, because that's what we're looking for, right? We're trying to identify this particular type of object. Okay. That's it. That's the only neural network jargon part of the presentation. Okay, so now we need to figure out, can our convolutional neural network spot a swastika? Can it help us with our Nazi hunting project? Now, this is the cool part, because if you're not familiar with neural networks or deep learning, this is the library for you. Trust me, it's the one that I used. So first and foremost, Careus. It's kind of like a high-level network, like a high-level abstraction on top of some popular libraries for neural networks, namely Theano and TensorFlow. So if you've heard of Theano, if you've heard of TensorFlow, if you've tried to use them, if you've played around with the tutorial, they're pretty low level. It's like you pretty much need to know how to construct a neural network yourself. They just help you along the way with some best practices, and that's fine, but frankly, that's way too complicated, especially if you're just testing out new ideas. And so Careus gives you kind of an easy abstraction to work with kind of common types of layers that you'll use all the time. And it's written in Python, which is the best programming language ever invented. Sorry. It's like I feel like it's a little bit of like a cheap gag with a bunch of technical people to poke at a favorite programming language. But there we are. Okay, so this is the neural network, the kind of convolutional neural network that I came up with using Careus. We don't need to worry about what all of these layers are. I'm not going to go into detail. It doesn't really matter. Basically, I had only 200 images, which is a tiny number of images. It's a tiny, tiny, tiny data set for working with a neural network, especially if you're trying to build a deep neural network. That said, even though I only had 200 images, I was still able to get to 80% accuracy, and I think this was like 5 epochs. After that, it stopped. My error rate stopped going down. So it's kind of remarkable that it's as useful as it is with such a small training set. That said, it gets even better. Because the cool thing about neural networks, the cool thing about this deep learning approach is that you can compose different neural networks together. So like I was saying, the way that a neural network is kind of looking at that kind of pixel intensity matrix, different chunks of it, and deriving features. And it's understanding which features allow it to make better classifications over time, like over many, many training epochs. That's cool because there are some people that have gone to the trouble of training very complicated neural network architectures on huge data sets. So this ImageNet data set has millions of images, and it has 1,000 different classes. So there's classes for cats and dogs and cars and lampposts and people, and there's like classes for like specific types of dogs and cats and cars, right? So it gets really deep. Yeah.
Are any of those databases publicly available?
Yeah, ImageNet's publicly available. Every year there's a contest, or sort of, like a kind of an academic contest, where different groups are trying to get the most accurate model to predict the different 1,000 classes inside ImageNet. And Visual Geometry Group, VGG, has been successful, the most successful for the last couple of years. And their network architecture and the weights that their deep learning model learned are publicly available. And they're so commonly used that they ship with Careus out of the box. So if you grab Careus off GitHub, you have a model that's pre-trained on 1,000 classes that will recognize with like 95 or 96% accuracy, something absurd, these different 1,000 classes. And it's just sitting there at your disposal, which is fantastic if you're trying to recognize objects that are inside ImageNet. Swastikas aren't inside ImageNet. So, the nice thing though is that you can basically say, hey, I want to take all the good work that you've done, thank you neural net, for learning all of those features that help you distinguish between different types of images, and I just want to add a little icing on top of that cake. I want to introduce one more class, and I want to see if you can distinguish between this new class that I'm giving you and everything that you already know. And I thought that that would be the way that I would use deep learning and look really smart at MIT. I was going to say, like, check it out, you guys. I found the best neural network available. I used the weights, I composed a new neural network, I trained it on swastikas, and now look, it's amazing. Except it didn't really work. So, so it was able to successfully identify the swastika when it was alone, right? But that's not really what we're doing here. We're trying to identify the swastika no matter where it appears in the image, because as we've already discovered, sometimes it appears like that dude flexing with his shirt off. And we have to be able to identify the swastika in that context just like we can when it's on its own. So as much as, and I think honestly the reason that it didn't work, even though I trained it on so many classes, is that, like, although you and I, like, we all look at this and we go like, whoa, that's a swastika. Like, that dude has a swastika right there on his chest, because we recognize we recognize this, and we have the historical context, and we know that this is a scary symbol, and we know that it's weird that like some bald-headed, scary-looking white guy is like posing with his shirt off and flexing, and like all of this comes together to make us think like, dear God, that man has a swastika on his chest. But the neural network doesn't really care. The neural network doesn't have an emotional response to this. It goes like, hey, I see a lot of things that I can predict in here. I know what this image is about. There's a man in here. There's a human. He's standing. He's flexing. He has a tattoo. There's a door in the background. I'm so smart. And that's great, except it doesn't really discover the thing that we want. So ultimately, deep learning has failed us. I'm sure that that robot did some deep learning. It's not just a totally gag slide. Okay, so deep learning, not super successful. Never fear, though, because there are other ways to go about doing computer vision. So this is kind of old school. It's like from 2011, 2012 is when this library came out. Back when smartphones were just barely larger than regular phones. When your watch didn't buzz, when cars couldn't drive themselves, when the president didn't tweet. So OpenCV is pretty cool. I think it's originally written in C++, but there's a lot of libraries that, or a lot of programming languages that interface with it, namely Python, the best language in the world. So there's a lot of cool things that you can do with OpenCV, not just the thing that we're going to do, and I'll get to that in a second. So you can go from like really very simple kind of computer vision problems. This template matching is literally just what it sounds. In a few lines of code, you can say, hey, if you spot this smaller image anywhere in the big image, let me know. Which doesn't turn out to be that useful, I'll be honest with you, but it is kind of a nice, easy introduction to what's actually happening, like kind of a simple technique for scanning an image. And if you were looking for like your company's watermark or something like this, it might be, it's a handy, quick and dirty kind of solution for identifying something in a larger image. You can also do background removal, which is pretty awesome. It's kind of like the opposite of template matching. So if you know that you have like a static background, you can look for shapes that show up on top of that background. Because when you remove the two, when you like kind of do a diff of the two images, you can spot something that wasn't there before, which is cool. So this is from, this example is actually from a blog called PyImageSearch. And I warn you before you go to PyImageSearch that the author of this blog will spam the crap out of you. Dear God. Like, I get tons and tons of emails from this guy, Adrian, who I think is well-intentioned and very smart, but he won't leave you alone as soon as you've been to his website, but the content is pretty fantastic. And so what he was doing in this blog post is that he recognized that his roommate was stealing his beer, or at least he suspected that his roommate was stealing his beer when he wasn't around. And so he set up a camera that was feeding him, like kind of feeding like a little Raspberry Pi machine. It was feeding him an image like once every second, or a couple images every second. And he was just looking for the presence of a person on top of a static background. And if he found the presence of a person in multiple slides in a row, he knew that there was motion in the room. And because he knew there was motion in the room, he discovered that his roommate was, in fact, stealing his beer. So it's a practical application of computer vision. With OpenCV. Okay, but back to the task at hand. So we're going to use something called a HAR Cascade Classifier. That's, oops, Alfred, not Afred. That's Alfred HAR there on your left. The person for whom HAR Cascades are named. That's him performing computer vision, even though he invented, most of his work was in the early 1900s, so there was no computer vision. Nevertheless, he can posthumously engage in computer vision and look for the swastika on that scary guy's chest. And we're going to talk about how he does it. So the way that we do that is that there's these things called HAR features. And this is an important part of a HAR Cascade classifier, as you might imagine. And HAR features are just like this. You're kind of looking for these patterns inside of an image. And you're looking for these patterns, where are we? Okay. So basically you're scanning through an image looking for these patterns wherever you can find them. You're kind of looking for clusters of pixel intensities that represent those features that I just showed you, kind of moving across an image. And this might sound kind of like a convolution in a convolutional neural network, which it is, sort of, but there's a huge difference. A convolutional neural network is actually learning those features on its own. It's basically figuring out, based on raw information, what is and isn't a relevant feature. It doesn't really know the difference. It doesn't really have a concept of an edge. It learns the concept of an edge over time. What we're saying is like, hey, I'm telling you, algorithm, I'm telling you, model, that these features will be meaningful to you, so go find them wherever you can. So it's a little bit more prescriptive, right? You're kind of adding your own bias, although they turn out to be remarkably effective in identifying or detecting objects. Okay. So there's a couple things to know. In the OpenCV library, most of this complexity is largely hidden from you. You don't need to worry so much about the next 3 slides when you're a practitioner. But I felt like it might be nice to give you a little bit of background on what's happening in the HAR Cascade classifier. So bear with me for just a second. This is just a setup to say, if any of this doesn't make sense, don't let this dissuade you from actually using this in your applications. You don't really need to understand the theory. Okay. So about a HAR Cascade classifier. So all those HAR features that I showed you are represented as a single value. And that matters because you have to perform a computation in order to discover that single value. And that single value is basically, you look at that pixel intensity matrix, you recognize this pattern, and then you subtract the white parts from the black parts of the image. Like if you kind of look down there, B plus A minus D. Simple calculations, you're doing simple arithmetic, but as we will soon discover, because HAR features are multiple, there's no like set size for a HAR feature. So even for relatively small images, like a 24 by 24 thumbnail, you're going to find like 160,000 HAR features, like a ton of them. And each of those features might require like a handful of computations. So you're pretty quickly talking about like millions of computations for every single image. That is really slow. So that's a problem. So we're not going to be able to use this classifier unless there's a way to get around these 2 problems that we have. One is that it takes a lot of computation in order to extract these features in the first place. And 2, 160,000 features is ridiculous. Like, could you imagine a feature space that's 160,000 in size? Like if you had 160,000 features, A, training would take like the rest of your life, and B, even when you had a new observation and you wanted to make a prediction based on that observation, you'd have to apply the weights, whatever the kind of the weight vector to your input on 160,000 things. Like there's no use for this. So we're going to have to find a solution for that too. So we have to figure out how to derive these features more quickly, extract these features more quickly, and we're going to have to figure out how to reduce this feature space because it's just much too big. Cool? Okay. So the way that we reduce the computation for extracting the features is with something called an integral image, also known as a kind of summed area table. So basically, conceptually, we're just doing all of the addition up front. We don't need to get into, we really don't need to get into this in a super fine-grained amount of detail. But the cool thing about this is that, if you look at the top table and then if you look at the middle table, you can see that as you kind of go along from left to right across that top row, you're just adding numbers, right? And you can do this in one pass at the very beginning. As soon as you see the image, you don't have to do it every time for every feature that you're extracting from the image. You just do it once. And by doing this, you reduce the amount of overall computation, or the overall number of calculations by about 50%, which is a dramatic reduction in the time that it takes to extract these features from the image. Okay, so that's pretty cool. Integral image, summed area table, fantastic. The second thing that we're going to do is to reduce the number of features in the feature space by discovering the ones that are the most valuable to us, the ones that actually will do the best at predicting the outcome that we need. Because surely in a feature space of 160,000 features, some of those are going to be redundant. Some of those are not actually going to provide us any meaningful information in making a prediction about whether or not the image contains the thing that we're looking for. And if you're not familiar with adaptive boosting, or ADA boost, or ADA boost, how does everybody else say it? Does anybody else know it? Who's familiar with this algorithm? ADA boost? ADA boost? ADA boost? All right. This is the problem with the technical profession. So, like there's a web server called Nginx. It's spelled Nginx. And I assumed that it was Nginx because Nginx is fast. And then I met somebody like 6 months ago, and he goes, "Do you use that web server? It's called Nginx." I was like, what? That sounds like the worst possible way to say that word. So this is why I'm confused, but we'll call it ADA boost. But it stands for adaptive boosting. And basically what this technique is that it's taking a really large feature space. And like I said, it's trying to find which combination of features is going to be the most helpful to us. So imagine like a super small feature space, like you had 3 features. And you said, is feature 1 helpful in predicting what I need to predict? How accurate? What's the error rate for my predictions if I only used feature 1? So you figure that out. You look at feature 2. If I only use feature 2 when making predictions, will my predictions get better or will they get worse? And if 2 is better than 1, maybe we can just get rid of 1. Then we look at feature 3, and then we see, do my predictions get better or worse? And you kind of see where this is going. And then you start to look for combinations. How does feature 3 work with feature 1? Is that better than feature 2? Yada, 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 yada. So it gets a little bit complicated. Fortunately, it's done by a computer, so you don't really have to worry about how complicated it gets. But the nice thing, the outcome of this, is that you end up with a bunch of these kind of like weak classifiers that you can use together, that you end up with a fairly accurate classifier with a dramatically smaller feature space. So instead of 160,000 features from this tiny little thumbnail image, you end up with hundreds or maybe a few thousand, which is a huge improvement. It's a much more manageable size. The last cool thing that the HAR Cascade Classification model does for you is that it cascades. So a cascade algorithm is one of those things where it's like remarkably simple, but then as soon as you see it used, you're like, oh my gosh, that's genius. Why didn't I think about that before? So let's say that there's 3,000 features to evaluate to decide whether or not this image contains a face. The nice thing is that there are some features that are absolutely necessary. If feature 1 isn't in the image, there's no way that this contains a face, so we can just discard it. So the model kind of goes through in like a hierarchical fashion and says, if feature 1 is present, okay, we'll go on to features 2, 3, and 4. If feature 1 isn't present, then we'll just abandon this and we'll tell you it doesn't contain a face. This doesn't contain the thing that you're looking for. Which means that when you're actually looking at new observations, when you're feeding images to the model and asking it to predict whether or not this image contains this object that you want to detect, it's remarkably more efficient. You don't need to evaluate 3,000 features every single time, which is pretty cool. So it ends up being pretty snappy. And in fact, like these 3 improvements that I just talked about, so even though you have this big feature space, even though extracting features is kind of computationally expensive, ultimately, this ends up being so fast that kind of high-performance computer vision applications, like the kind of stuff that like Google's doing with self-driving cars. So they use a lot of deep learning in their computer vision, the kind of real-time computer vision for like autonomous vehicles. But they're starting to bring back Cascade classifiers, Cascade algorithms, because they're so fast, and using them in concert with their deep learning algorithms. I won't profess to know how they do that because their academic papers are really confusing. But if you do have a background in machine learning, you might get something out of that. But basically the point being is that even though we kind of went to great lengths to explain how these things work, the takeaway is that they end up being pretty snappy. Okay, so I feel like I'm talking kind of fast. Hopefully it's not too fast. Okay, so we start with this pixel intensity matrix. We create our little summed area table. We extract our HAR features. We use ADA boost to determine the most informative features. And then we use that cascade algorithm to basically decide whether or not we need to continue evaluating the features in some new image that we've discovered. And in that process, we make a prediction. And it's kind of like this. You basically move across the image, and then you decide, you're looking over and over and over again, is the shape I'm looking for in here? Is it 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 in here? And for the most part, the kind of most common use case for the HAR Cascade classifier is in detecting faces, detecting the shape of a face. Which is why this is the example that we have, because I stole this GIF from somebody else. But that's not what we're doing. So I should point out that, like, if you do want to detect faces, if that's your use case, which will be pretty common, OpenCV comes with that out of the box. There's a classifier that's already trained on faces. You import it into your Python module or whatever other language that you're using, and then you immediately have access to it. It comes pre-trained, so you're good to go. If you're trying to detect any other shape, then you have to train your own HAR Cascade classifier, which is a little bit complicated. So But just as a reminder, this is our task. We're trying to pull out swastikas and identify them even when they appear in kind of like, strange context, and distinguishing between them and other kind of like heavy, graphical, iconic things, all the other kind of hate symbols that are floating around in this space that we will definitely run into because our entire data set, or a large part of our data set, will be full of people who post this kind of stuff in their Twitter profiles. Fortunately, when you go to train a HAR Cascade classifier, there's an app for that. There's an open source library for that. I'll put these slides online so you all can have access to them. But this takes what would otherwise be a relatively complicated process and makes it really straightforward. So in effect, the way that you step through this, it's like every other model that you've ever trained. You have some positive examples and you have some negative examples. In this case, you need a remarkably small number of positive examples for the complexity of the task. I went through, I cropped a bunch of swastikas. You're basically just looking for the shape itself. You don't need to show the image in context, you just need the shape. I've had about 60 images because I didn't have a lot of time. I wasn't gonna go through cropping hundreds and hundreds of swastikas until I cried myself to sleep. Just wishing humanity wasn't so horrible all the time. But yeah, with only 60 positive examples, which is a tiny, 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 tiny number, and I think maybe 300 or 400 negative examples, I was able to feed the training data to the model. The other thing that this library provides for you out of the box that you probably could figure out how to do on your own, but it's a nice handy kind of a handy tool, is that it does like lots of image transformations. And so this is a kind of, when you're classifying images, this is a relatively common tactic. You do lots of transformations of the image. You kind of stretch it a little bit, you rotate it a little bit, you invert it, so that when you're so that way, even though you'll likely see this image in kind of different distortions or in different contexts when you're really looking for it, it's more likely to be recognized because you've told the algorithm basically that this shape that you're looking for might appear in lots of different, slightly different ways.
I don't know, curious.
Yeah.
So 2 slides back when you had the positive and negatives,
Uh-huh.
what are you looking for in terms of a choice for the negatives? Because I mean, maybe my vision's bad, but that's just some guy.
It is just some guy, but that's how I did it. Like I just picked a bunch of random images in which I knew the swastika would not appear.
Oh, okay, gotcha.
And that's it. Yeah. I mean, really anything whatsoever, because you're basically trying to give it as clear of a distinction as possible between like this is a shape, this is a distinct shape. You're probably like learn the features that make up this shape that don't appear in anything else. You know what I mean? Yeah. Which is a good point to bring up. Like in other machine learning contexts, you might be looking for kind of like close examples a lot of the time. You might say that like, if let's take a completely different example and say that you're trying to predict the difference between, you're trying to use like the content from my social media profile and predict whether I would vote Democrat or Republican, for example. And so in order to do that effectively, you'd probably want to use data from people who share my social media habits and who post maybe as often as I do and post about the same topics as I do and whatever, and try and find people who post like me but are from the other political party. So you want that kind of close example to make sure that you're really doing like a fine-grained distinction, that you're distinguishing on the important aspects that make me different from other people. That's not the case here. You're trying to say like, you're trying to isolate this shape and give as kind of a clear definition as possible that this shape is different and unique, and that allows you to be able to identify it in other contexts. Like you're looking to be able to identify the shape, learn the shape, not so much learn to distinguish the shape between things that are kind of similar to it. Yeah?
The person is totally, completely different. Why would you not use other symbols, for instance?
Like crosses.
Yeah, they're in the data set as well. But ultimately, I think that although it might, the kind of things that appear like they're similar on the surface to us, like if we're even kind of getting into the details of what's, like it might be that there's shapes that are kind of swastika-esque or like little kind of corners of his shirt or things like that I think would read to the machine in the same way. So I think in this case I've had success just being clear about the thing that I was looking for and kind of not really worrying about what else I was feeding the model. Yeah?
Did you have troubles with false positive rate? I mean, I would expect that this would handle the negative cases, but the false positives could be potentially bigger than with like the neural network. And so I was just curious if you found that or if you were able to address it with enough negative cases.
I did have more of a problem with false positives with this than I did with the neural network. It was, and we'll kind of see, it's remarkably good at discovering it, but then it saw it where it wasn't. And I think it's kind of an internal debate with me about whether it's because this is a shape that's pretty easy to find in a lot of, you know what I mean? It looks like an iconic shape to us, but actually something with those sorts of edges. Like I said, like, you know, the corner of somebody's armpit, you know, kind of almost gives you that shape as much as a, or whether it's just that I just didn't have enough samples, and that maybe if I had a larger training set or gave it, you know, I think I did like 20 training epochs that we'll get to in a second, but if I'd done 40 or 50, maybe it would have been able to make a finer grain separation. So we'll see. We talk about this, sort of creating the permutations, and then this is it. There's sort of a nice sort of catch-all method that grabs your training data, accepts some parameters like the width and height of all the images that you feed it. All of the images need to be the same size because your kind of feature space always needs to be the same. The shape of your input always needs to be the same. And then this will run for about 24 hours. It takes a really, really, really long time to train. Which makes sense when you kind of think about what it's doing. So it's extracting, you know, hundreds of thousands of features from all of the images that I fed it, because I wasn't feeding it 24 by 24 images, I was feeding it like 80 by 80 images. So it resulted in a huge number of features, and then that adaptive boosting algorithm, while very effective at making accurate predictions, takes a long time to figure out. Because if you could imagine, even in the example that I gave you, the kind of toy example for AdaBoost, it was difficult to explain how that would work with 3 features. Just imagine how complicated it is with 100,000 features. But the nice thing is that it spits out model weights into an XML file, and then once you have that XML file, it's tiny, its footprint is tiny, its memory footprint is tiny. When you pull it, when you use the XML file to like load the model back into memory, basically, into RAM, it's really small and it's really performant. So getting in and out of memory is really straightforward. It's just this training process takes a really, really long time. So it's kind of a set it and forget it sort of thing. The nice thing, though, is that it does a remarkably good job. So there's all sorts of little things that I think are worth pointing out here. So like that woman's hat, you can sort of see at the top, the swastika is slightly warped because it's on a curved surface. The same thing on that kind of anime character's shirt. It's like at an odd orientation and also a little bit warped because of the position of her arm. On the back of that guy's neck, his tattoo, the corner of it is actually hidden beneath the collar of his shirt, but it was still recognized. Also, there's a little wave because of his, like a fluctuation in his skin. But that it was still recognized in any case. What else? That's sort of and then again, the swastika that is the larger swastika behind the anime character's head is partially obscured by her hair, but was still discovered. So it's accurate, and unlike the kind of the neural network that we trained, it's able to identify the shape in context in a much more fine-grained way, which turns out to be pretty useful.
It didn't find the one on her shoulder because one of the legs is actually.
Yeah, that was too obscured, so it didn't find the one on her.
But it's going the other direction.
Yeah, that's the one you don't want to detect. That's the Buddhist symbol for eternal life.
That's true. That's my assumption with the guy in the middle, that he was just confused, like, because otherwise it doesn't make any sense. But no, you make a good point. And yeah, that's true. That one was a little bit too warped and a little bit too obscured, so it didn't catch it. So.
To the left, there not
going the other
right,
direction.
so it's going on.
Well, that's true. I mean, I did actually. I fed the classifier ones with it reversed just for this context, like because I was purposefully being pretty aggressive because I knew that I was looking at a data set of people who were all more or less connected to each other on social media and seemed to have an interest in white nationalism. So I was like, well, look, if this image turns up in any way, even if it's inverted amongst this group of people, it's probably not because they're like peaceniks doing yoga. You never know. You never know. I don't know that many white nationalists. So, wait. Here, I'll go. Here, go. We'll go here.
The slide where you showed the different warped versions of it,
Uh-huh.
the comment said it took care of cropping for you. Did it recognize like half of the swastika?
It didn't recognize.
Didn't hear it yet.
Yeah.
Never happened.
No, I didn't find any.
In the training data,
Yeah.
that when it got done doing the training,
Mhm.
you visualize that data and see any logic to it, or is it just like a random pile of numbers?
It's just weights in an XML file, like the way that the input vector gets weighted. So not, I mean, I guess if I looked at the file, there might be a way to visualize it that would be meaningful, but I don't know that it would make sense. As far as I know, there aren't tools for kind of visualizing the different training steps and the way that people have been developing them for kind of deep learning models.
Were you able to take when you had a false positive or positives or negatives even and say, no, that's actually a swastika, no, this is not a swastika. Now feedback, close the loop with helping the system, improving the model by giving a feedback reinforcement.
Yeah, I don't believe that you can do reinforcement learning the way that this model is implemented. That kind of like incremental improvements, I think you'd basically have to rebuild, you'd have to kind of refine your training set and then build the model again. A chance to jump in.
Yeah, I was just curious. So it sounds like you're saying this was surprisingly robust to like size, rotation, and tilt.
Yeah.
And so I'm curious if you tested the boundaries of that at all, and whether or not you think it would hold up for other symbols.
I do think it would hold up for other symbols, mostly because this is like I said, this is not a very complex symbol, so there's not actually that much that distinguishes it from kind of random noise. And I didn't test the boundaries to see how far I was basically just skimming through the images that it discovered and saying, like, does this account, like,
Yeah.
you know what I mean? Like, you discovered a swastika in this Twitter avatar. Is there really one there? And B, is the profile that this image is associated with what I would expect based on the fact that they posted a swastika online. So, but I haven't kind of tested the boundaries to see how far you could.
I would think most of your subjects are like proud of the symbol, so they're not trying to obfuscate it.
Right. I mean, sometimes it's obfuscated, like just by like a matter of course or whatever. But yeah, it's true. It's not like they're trying to hide it. Like you would kind of wouldn't put it there in the first place if you were, you know what I mean?
Ha!
Right. I snuck it in there. What you didn't realize is that technically there was a swastika on my profile the whole time. Yeah.
Question?
Yeah.
What was you may have mentioned this, what was the total size of your positive and negative?
I had about 60 positive examples, and the reason that was so small is so if I was training this on an object that wasn't quite as uniform, like a face, for example, I would suspect you'd probably need hundreds or thousands, really, even for this type of approach. But there's really only so many ways to crop a swastika. Because it's a relatively concrete symbol, so I had 60, and then I honestly don't remember how many negative examples, but it was 400 or 500. Like it was a decent size.
It's still very impressive that you're getting these kind of results out of such few examples, even for such a simple symbol.
Yeah, it was pretty surprising, So I think if you have the time to wait for, to wait for kind of 20 epochs to run for this kind of thing. And like I said, that took 24 hours. I ran it for 20 epochs. What I didn't try, and I probably should have, was for something this simple. Maybe I could have run like 5 or 10 epochs, and it would have been just as accurate. Like I didn't actually learn anything from those extra 10, anything meaningful. So, yeah.
Which was your test data set, and talked about your confusion matrix, false positives, false negatives.
I used the entire data set And then then what I did was I had like 20,000 accounts that I was monitoring, and I looked for any time that it was discovered, and then that pulled about 200 images, and this is all off the top of my head, pulled about 200 images, and there was maybe 10 or 15 false positives, and I don't know in the data set how many swastikas I missed that were in Twitter profiles.
So it was a discovery.
It was more of a discovery, yeah.
After collecting your test set, does you think you're a white supremacist?
You know, I wonder about that. Like, people who do this kind of work joke a lot, you know, because you end up like collecting a lot of data about like ISIS supporters and other kind of, you know, extremist groups. You tend to get good at it where you just end up like creating fake accounts and things like that to keep an eye on people, or like using RSS feeds that pull them out of Twitter and like monitoring it through some other service, as opposed to actually, you know, just hanging out with these guys directly, for lots of reasons. But yeah, exactly. So yeah, but you never know. You never know. Actually, the funny thing is, so there's as a totally separate thing, what does happen sometimes, which is kind of funny, is that when you are viewing accounts, so you're not actually like following people or putting them on lists or whatever, so they don't know who you are, but you're just looking at their page as an observer. And Twitter's always suggesting like other accounts that you should follow, like, oh, so hey, if you're interested in this person, like here's a bunch of people that are like them. And so it's this kind of weird little like behavioral reinforcement that these social media platforms do, where it's like, hey, you seem to be interested in white supremacy. Here's some more of it, you know. But it's, I mean, like we're joking about it, but like there's been this talk about filter bubbles and like echo chambers and things like that, and that's the reason that these things exist, is because the social media companies are designed to give you more of what you already seem to be interested in. So if you're like a super lefty liberal, then all it shows you is like super lefty liberal content, and you think that the entire world is super lefty liberals, and then you get really surprised when Donald Trump is elected.
Maybe a way to find your false negatives.
Yeah, that's a good point. So yeah, I think like in the more like academic context, I think a more like a responsible thing to do probably would be to so I had other means for identifying like extremists, white nationalist accounts that weren't just based on image recognition. So I was actually also looking at the content of their Twitter profiles, which was usually pretty clear. Like people were openly declaring themselves as being like National Socialist, which is like Nazis. And so it's pretty obvious. And I found 3,000 accounts that way, only a couple hundred this way. It was a couple hundred important accounts because all of these accounts were like pretty extreme. And often these were the accounts that were talking about like making direct threats of violence. So it was helpful in the end. But I think knowing that there were only 3,000 accounts that I had identified with the text in their profile that were probably extremists, it wouldn't take that long to scan them quickly and just see whether or not any of those contained swastikas that were missed by this algorithm. Yeah. Oh, sorry. Sorry, we'll just go back there for CS info. I collected data. Well, I collected data over the month of August. So I had data, but the data went back until January.
The follow-up question is, you used the term earlier to get our interest called the alt-right.
Mm-hmm.
And as far as I could think, that wasn't visible until just recently. Even this month,
they've really come into the public eye recently, especially now that Steve Bannon got appointed to the cabinet. But they've been active for some time.
You had a way of determining they were back in office.
I did, yeah. So there's a just because it's of interest, the way that in the same way that we went about finding ISIS online, people who are in these extremist communities tend to be pretty insular because they're, because in the same way that they all want to post images to say that they're allegiant to a group, they all share this kind of bizarre worldview. And so if you share a bizarre worldview with somebody else, you tend to hang out with those people all the time. And so we developed a metric that looked at the degree to which you participated in a network. And so we'd find like 100 or 150 core accounts that we'd manually identified as being associated with an ideology, and then built out a large network from there, about 1 million accounts, and then looked at the subset of those that were kind of like highly connected and then participated in that dense community, and then we gave them a score. And so that was one way that we went about determining like who was and who wasn't associated with a particular movement.
That we was not you.
In this case, this was me. When we went on the ISIS research that I did, that was me and a guy called J.M. Berger, who's like a terrorism expert.
I'm just, look overall in this whole area, just the SME
Mm-hmm.
and the normal breed. I can't understand that. The code stuff you have up there. At some point, it seems to me you need a team like that.
I think so. The mechanics, so as a separate conversation, I guess, like the mechanics of extremist communities operating online are pretty consistent. That was sort of an interesting discovery here, is that the way that ISIS operates online is remarkably similar to the way that other extremist groups like the alt-right operate. They're kind of very dense, they're hyperactive, et cetera, et cetera. But then to be able to make to be able to determine who should and shouldn't be in kind of like your training data set, it is helpful to have like a SME, like a subject matter expert who really understands the kind of offline implications of the research that you're doing. And so with the ISIS work, that was JM. With this, I have more of a background kind of understanding these folks, but we've also kind of exchanged ideas like the Southern Poverty Law Center and like other people who academically and like qualitatively study these sorts of folks.
Another type of question, which some of this analytics stuff is reading back here, and that's the old-fashioned, here we used to call it, one of their association name is competitive analysis. I think that's one of their terms. But that whole group that we use, Google,
Mm-hmm.
or even scraps in garbage dumps, the old spots.
Oh yeah. Are you like opposition research?
Yeah,
Like
we had, when Cemetery came here, they started a good-sized skip group. That's the Systems Competitive Analysis group. And you're nodding your head like you know. They have had their meetups, their meetings, and now it seems to be a very low level. But at one point they were national. They had a huge group, and they would use more text analysis.
Mm-hmm.
But that's another SME type. It might be useful.
Yeah. Cool. The skip like SCIP.
Yes.
SCIP. Yeah.
Okay.
Strategic Competitive Intelligence Professionals.
Thank you.
Ah. All right. Cool. Like private sector analysts, kind of.
What's left of industrial espionage.
Yeah.
Oh, excellent. Okay. Cool.
That was why they were brought in. Cemetech was formed, if you know any of Austin's background.
Okay.
So maybe 25 years ago, for fear that the Japanese were going to overtake us.
Awesome. We should talk more about this because I'm interested, but I don't know if everybody else is into the is into the analyst stuff. Yeah.
But some of this makes me wonder about here, particularly the libraries. Unfortunately, I don't know how big the libraries are computationally, but putting this into an FPGA, or at least part of it or the whole thing in an FPGA, and getting an 8 times 10 or better speed improvement.
I think that it probably would. I don't remember specifically whether or not you can get like whether or not these algorithms would be accelerated in like a distributed computational environment or like accelerated by the GPU. Yeah.
And what you usually have to translate to VHDL or Verilog, there are FPGAs or programs that let you use straight C.
I wouldn't be surprised. I mean, OpenCV is written, like I said, in C or C++, and so it just depends on whether or not you'd have access to that kind of optimization through the Python bindings. But I would assume so.
But this is all new to me. I don't know how big the routines are.
Yeah. Yeah, man. Here, we'll go here and then back.
Yeah, they're,
sorry.
most of these are GPUs. Most of these algorithms, I'm quite sure report well to GPU, if they're not already, right?
Mm-hmm.
And as far as FPGAs, there's some development in that era for FPGA doing both machine learning and classification, and then, really the machine learning part and then the classification. You can apply the same FPGA to both. You just don't need the complexity for the actual classification part that you need for machine learning. Right? So there's some development in that area, but I'm not aware of any. You know, there are a few commercial products. IBM has one. There are a few other people that have them, but they're not really, wouldn't classify them as mainstream. Most of it's in GPUs right now, and they're doing millions of photos, and something like this would be sped up, orders of magnitude most likely.
Yeah, I would assume. I mean, this was just running on my 2013 MacBook, so
yeah.
It wasn't. Yeah, sorry. Did you have? We'll go back, but here first.
Did you do anything to do a timing analysis on the epochs when you were training the cycle? Did you know if they were getting longer, if they were consistent from epoch to epoch?
Anecdotally, based on observation, they seem to be about the same. It didn't seem as if there was any performance improvement, because I guessed 24 hours after watching it do a couple, and it was about 24 hours exactly, so it didn't look like there was any change in the training time.
Just kind of as a follow-on, is there any way that you can do kind of seeding for weights?
Maybe.
Because with a symbol like this basic,
Mm-hmm.
it'd be something that you and I could sit down for 5 minutes and say, like, a little diagonal line, that's probably something that's going to be useful. A little horizontal line is going to be something that's useful. Right?
Mm-hmm.
So you could initially seed it with something that has those kind of weightings, and little circles and squiggly lines are probably going to be less interesting, so you can kind of stack the deck.
Yeah, that's a good point, actually. My assumption would be yes, but I didn't look into it. But I bet you're right, actually. That even if you could kind of arbitrarily or preempt the feature space and say that we're looking for these sorts of the HAR features that are available, we only want ones that are like X, Y, and Z. So, yeah.
To follow up on your GPU, about 6 months ago, an IBM engineer spoke downtown, and there are more and more newer and newer architectures coming with using the power chip. So this could be a powerful application. I don't know about the FPGA. GPUs, which are coming down in price.
Yeah. The new kind of semi commodity machines that you can have GPUs on now. You can get 4 GPUs on a machine that's less than $1 an hour, I think, on AWS. Yeah, which is pretty significant. In the back.
You mentioned Amazon, and since we're here, I think that's a really good point. You can rent a P2X large for less than $1 an hour, and it's got a K80 in it.
Mm-hmm.
Given how cheap GPUs are, do you see that the HAR Cascades are going to become less useful as GPU computing gets increasingly cheaper?
I think that's really valid. I mean, I think even in the description for the talk, I mentioned how it can be kind of expensive, especially if you if you have some of those larger machines with lots of GPUs running for 24 hours a day, I don't mind, $50 here and there.
Well, you mentioned that you trained originally on the 2013 laptop, but a K80 training on a small data set like this should probably go pretty fast.
Yeah, I agree. It would probably be even faster. Sorry. Yeah, absolutely. The other reason that it's useful is the size of the training data. In this case, I would have had to find probably thousands of examples or tens of thousands of examples of swastikas in different contexts that I didn't have time for. So there's another trade-off, the other deep learning trade-off. But I agree in terms of actual computational costs. It's not cost prohibitive anymore. For these kind of modestly sized models,
I'm curious about the pre-selector, the thing that was throwing away images that for sure, quote, didn't have a swastika in them. You mentioned early on that there was a thing that you'd go through and say, okay, if this doesn't have these prerequisites, we won't take it to the next step to process it for a swastika.
Oh, the Cascade algorithm?
Yeah, I guess I don't remember the name.
Yeah.
But I was wondering how effective that was. Did you fed it 100,000 images and it threw away 90,000? And did you evaluate it yourself to see how well it was performing in terms of rejecting the images so that you could save the processing effort?
I don't think I explained that super clearly. It's more that so those individual HAR features. So you might after you kind of go through that process of using adaptive boosting to discover the feature space that's most relevant to making accurate predictions. So let's say it's like 1,000 features. That cascade process is actually going through and evaluating the presence of the most important or an essential feature in the image. And if that essential feature isn't there, then it discards the image, if that makes sense. So okay.
That's what I'm asking.
Oh, okay. I think the only way in which I would have evaluated that, and I didn't, was to look at the 19,800 images that it said didn't contain any swastikas and evaluate how many of those actually did that were missed, and then I would know that I had a problem somewhere potentially, and that the feature that was identified as being essential, or some high-ranking feature, was perhaps not as essential as the algorithm had determined, but I'm not sure.
I would suspect that your results were not, it's not a true or false. This is not likely to have a swastika, and this one's highly likely to have a swastika. Is that right? You had thresholds and levels of correlation.
Sort of, but in this case, it actually is. It is more binary. Like you either have the coordinates of the location of a swastika in an image, or you don't. It's like not so much like you would get with a
kind of scoring results.
Not like you would with like a neural network or something where there's like a certain degree of confidence that the thing you're looking for is present.
You could go through and look at the ones that were like 80%. Okay, no, those are actually pretty good. Let's bring the threshold down. Even at 80%, it's very unlikely there's a swastika. Let's move it up.
Mm-hmm.
You didn't have that kind of control in this scenario.
No, I didn't. But I agree. That would be and I think in the training phase, I think that there's different kind of like knobs that you can tweak. That having gone through this process one time or a couple times, I think that's probably where you'd make some of those adjustments, where you'd run it with maybe a smaller number of epochs, like 2 or 3 training epochs, so that it takes like 10 minutes instead of 24 hours or whatever. Evaluate your kind of level of success, tweak some of those inputs, and then run it again until you got to the point where you were kind of felt like you'd optimized it as much as you needed to, and then run it for the longer period of time.
It seems to be really interesting to find that threshold where it's really not a swastika,
mm-hmm.
or it is. Find that threshold and look right at that boundary for useful information.
Yeah.
I think it would be really interesting to see those images.
Mm-hmm. Yeah, I agree. Yeah, and to start to understand what it was that confused it. Absolutely. Yeah.
Is there a way to apply the HAR cascades in Fourier space, meaning in frequency space, so that actually this would be invariant to the rotation and those kind of transform? I don't know if there is some studies in this direction.
I think there's a HAR wavelet.
There is a HAR wavelet.
Yeah.
Created by the same guy.
Okay.
Yes. But I haven't looked into it, so I don't know how any of them work. But I would assume so. Although we should probably point out that the HAR features are like named after that guy. He wasn't really doing like image classification in like the early 1900s. It's more of like an honorary. Anyway, all right. All right. Any more questions? Cool. Thanks, everybody. Oh, wait, one more question. Yeah. Yeah.
You were doing your deep learning. Cool stuff. Looks real fun, Jonathan. But like when you're doing your deep learning, next time, maybe try and just remove the entire top layer and just train on swastika, not swastika, and you won't have that problem that you had, right? So you had like things that had higher confidence because of whatever the sigmoid stuff is, right? And so that ended up higher. But if you actually just remove the entire top layer and trained on swastika, not swastika, I think you've got a lot better results with the deep learning.
Oh, interesting. Okay, cool. So like use the pre-trained network, but then remove the
just remove the entire top layer. You can use the one you had, or you can use the Inception stuff from Google and just like take the entire entire top layer, and you can, because basically that's what you did with the R's, right? You had
Yeah.
positives and negatives,
Mhm.
so you just had your two classifications, and then you get your confidence number and all that stuff too. So,
Oh, interesting.
and that I think would end up giving you most.
Oh, cool. Thanks. That's
Just try that.
yeah. I'll give it a shot. Thanks, man. Cool. All right. Thanks, everybody.